Thank you so much, everyone. Thank you so much for coming to this talk. Today we're going to be talking about simple recipes that will help you to accelerate the builds. And we're going to be talking primarily about Android builds and talk about the acceleration of the builds. Nothing else, particularly. So, about me. I have been an Android engineer for over 9 years. I am a Google Developer Expert for Android, Women Tech Makers Ambassador. I do not know, maybe I will get all other titles later on in my life. But currently, I work as an engineer at Toast and tech lead for POS productivity team. So today, I want to share a story of how we at Toast analyzed, researched, and ultimately optimized our builds using these simple recipes, which might seem like one-line changes, but they come with a big and heavy research lift behind done by my team and me. So, and today's agenda will be, we talk about why we need to care, why we care about the build times. We talk about what kind of bottlenecks we experienced at Toast, specifically with our main app, and what kind of fixes we put out there, locally and remotely, what we learned out of that, and we're just going to recap, share some helpful plugins, and so on, that you can use to learn more about your own builds. All right, so to give context, Toast is a POS company, right? Point of sale company. Many restaurants use it on daily, day-to-day basis. Toast has lots of different apps, but the main app is a POS app that is used directly in the restaurants, right? And it's an Android app. This app has over 2 million lines of code, 294 modules, and right now we are averaging at 150 builds a day with 110 contributors. The number of contributors used to be higher last year, but I'm giving talk today, so, so it got less. When it comes to build tools, specifically, there are 4 tools that we use. Gradle is our build system for our Android app. Git is our version control, right? GitHub to host that version control in our repository, and Jenkins, our CI solution. And today I'm going to be talking about what kind of fixes we put in different tools and how we leverage to make it work. All right, so the slowdown in build times, essentially it means the feedback to developers is slow, right? So, which means because the builds are slow, means that the feedback is slow, means less builds are being built, which often means the release cadence ends up being very slow. Those engineers know when you have a very long build, especially on a release cut, it gets really difficult to get your changes out the door, right? And imagine now if you have a hotfix that you need to get out the door and you require many loops to get out. It usually, even if it's a 1 null pointer change, it requires you at least a day, to put out there. So I compiled some data back in 2022. By the way, Toast, just like any other big startup, IPO'd in 2021, it IPO'd, and then it actually saw huge hyper growth in the number of customers that they got, in the number of engineers that joined the company. And so what happened is, in 2022, there were 62 contributors to Toast Mobile, our POS app. In 2023, the first half of the 2023, there were 141, so we saw a 227% increase in number of contributors. When you have more contributors, it means more features are being developed, more builds are being put out, right? And so number of remote builds went up from 4,306 to 13,000. In 2022, the entire year was 4,000, over 4,000, and the first half of 2023 was already 13,000 builds being built, right? And what essentially it means, because you have a lot of builds, there will be eventually a build queue congestion, which means the average build times might end up increasing, right? There's also a lot of other reasons why build times get increased. We're going to go down this rabbit hole later. But the build times in general also went up from 51.5 minutes in 2022 to 73 minutes in the first half of 2023. Again, with this kind of slow feedback loop, it means developers are paying that penalty and have very high context switch happening. And so the slow build times were very huge pain for developers, right? And that's why our team decided to prioritize the build acceleration as a main goal and main priority for second half of 2023. And this is where product developers saw a lot of different changes coming down the pipeline and waking up to surprise about, oh, something changed, what changed, right? And today, we're going to be focusing more about just the build times. Nothing else. We're not going to be talking about how you're going to set up your CI, what kind of quality gates you need, how can you improve the performance, and so on, just about the build times. When it comes to bottlenecks, especially related to build times, there are local and there are remote bottlenecks. Good thing is, if you make a modification and you update and resolve your local bottlenecks, local in terms of in your project itself, that you can run in your local machine, you can run in a remote machine, right? So when you address those problems in local, it will automatically apply to your remote changes, remote settings as well too. However, there are tweaks around as well within the remote. So let's go down with the local bottlenecks that you might experience. So there are three major bottlenecks. First one is optimizing Gradle properties file. You know, each Android project comes with Gradle properties, and Gradle properties is essentially a information about what your build system, in this case Gradle, need to know about how to run your project. That's the one information, right? Second bottleneck is unused dependencies, and third bottleneck is outdated dependencies. All of those three bottlenecks are like the main and major reasons why your build locally can slow down. One call out, when it comes to Gradle properties file, what you want to make sure between the settings, the key itself, and the parameters, there's no space. Otherwise, the settings that you're going to apply might not be applied, right? And you might spend hours and hours debugging, trying to understand why, when you change the value, nothing is being updated. Think of it as an internet permission. You know, like whenever you start a new Android project, you think everything is good, but you run the app and you get the crash because you missed the internet permission. So that's something about Gradle properties to keep in mind. So the first win, easy one-liner win, is parallelizing tasks, right? Running tasks in parallel always faster than running them sequentially. This is how math works. Doesn't matter. If you have 5 tasks, right, each of them take 5 minutes, sequentially it's going to be 25. But if you have 5 tasks, one of them takes 10 minutes, the rest of them take 5 minutes, the total amount of time will be, how many? 10, exactly. So you do need to enable parallel. By default, by the way, it's turned off. It's going to be false, so you do need to modify the Gradle properties file and turn it on. So basically, when you turn it on, you will allow Gradle to build projects in parallel, all of the sub-projects. The second one-liner win is cache, right? Caching is a fundamental concept and implies reusing previously executed tasks. And Gradle leverages incremental builds and the build cache in place. So whenever the Gradle fingerprints each task's input, it stores the outputs and then applies those outputs throughout different builds. In the local example, it's going to be to your next build. There's also one caveat about what it means to having monorepo, what it means to having a single module, like app module. Caching might not necessarily be a actual win, might not be a big win for you. But if you have multi-module, there's higher wins you can get from caching. in place, just because of the way how dependency graph is built, and you have different modules depend on other modules. So if you modify something on the top module, right, everything that is being executed on the bottom modules, the results being saved, and your top module is going to be just reusing those values. So now we finished with two-liners, one a touch base and another one-liner change, but it requires a little bit of thought around this time. When your application grows, when you have 2 million, 1 million lines of code, right, it gets complex, right? It creates more objects. Like when you hire new teams to build new features, you create new data classes in it, right? You end up building more and more features. Application gets complex. More objects are created in compiler, right? Which require extensive data processing itself, which in return require more memory to process that data. That's why memory configuration is the most important setting you can do to accelerate your builds, whether it's local or remote. With memory configuration, you need to focus on heap specifically, which is responsible for reducing that time in garbage collection and maximizing the throughput. Throughput is number of transactions per second. So you can set the heap size inside the JVM args setting. So JVM args settings, heap size, and make sure there are no spaces after the equal sign or before the equal sign. Otherwise, Gradle is going to disregard, and Gradle is going to set their own default values. If I'm not mistaken, in Gradle, I think heap size is 500 megabyte. I might be wrong. Something very low, which is not realistic to any production apps nowadays. One note, that you can pass many arguments inside the JVM args, right? Like so, after this one, you can pass the second one and third one in one line. But what you want to make sure is, if you set like this, setting just heap size, JVM args will end up defaulting to the regular, like let's say different argument, which is metaspace, right? So, which again, default version of the metaspace is much lower than what you need to do in your production app. Keep this in mind. Max heap size, right? It's called XMX, and it's responsible for the maximum throughput, maximum number of transactions you can get per second. And XMS is responsible for initial heap size. Setting initial heap size parameter is important because it reduces the need for JVM, to dynamically resize the heap itself, which can involve additional garbage collection cycles all the time. When in Android, production apps on Android are very hungry. Gradle is very hungry, and oftentimes you do end up using high number of heap. Like you do need very high number of heap size, like oftentimes. So what you want to do, you want to set the initial heap size to be around 80 to 100% of what your maximum heap size is, right? Because the truth to be told, Android apps are heavy. So especially if you have multiple modules, initial heap size needs to be high. Now, that's for initial heap size. It should be between 80 to 100% of your maximum heap size. When it comes to maximum heap size calculation itself, this is where it's going to get tricky. One way to think about that, how would you set your maximum XMS size, is to think about what is the most hungriest tasks. Gradle Enterprise, the velocity usually has interface, like the plugin that you can check what is the amount of tasks being, like how many gigabytes each task eats, and what's being used there. So by validating and reading that data, you can define and identify which of the tasks is longest. Oftentimes it's like app module. It's going to be the heaviest one, and specifically fingerprinting in it, right? So whatever the size it is for that task, set to be your maximum heap size. In our community, what we usually say is set 90% to be, like XMX, the maximum heap size, and the rest, and the rest of the 10% we should leave out for the native memory stuff. But what I learned, at least from our example, maybe something that we have not yet optimized on our end, but the thing is, most optimal way for us is that maximum heap size was 70% of the available memory versus and leaving the rest of the 30% of memory for metaspace and the other native memory. So that was our sweet spot. It might be different for different companies because your project might be a little different. But so if the community says 90%, ours is 70, so you can think about it something between 70 and 90. And if you set your XMX too low, what happens is your application will run out of memory, and you're going to get out of memory issue. But if you set it too high, you end up wasting resources, and you might not get enough memory as well. So identifying that the right size of XMX is sort of a game of trials and errors, and is different for different projects. This number worked for us. And by the way, we're going to come back to the heap size, maximum heap size calculation in our remote bottlenecks as well, too, because it affects a lot the way how we set up our remote agents. Now, look, another local bottleneck is Gradle workers. If you don't set the Gradle workers inside the Gradle.properties, by default, they will take up all available cores. So if your MacBook has 16 cores, Android Studio will, like Gradle, will end up running and taking up all of those 16 cores, which means your hardware and all of the, like, let's say, Google Chrome and Slack and so on will not have enough space to run, or other processes, OS processes that need to be run, right? Because otherwise, Gradle end up taking all of these cores. Another thing is some CIs, they report X number of cores. They say there's 32 cores available, 32 cores are there, but in reality, the available to use is half of them. So there could be a misrepresentation of numbers when it comes to CI cores. That's something to keep in mind as well. When this kind of things happen, usually you end up hitting out of memory issue on your device. Bless you. And so what you can do to resolve this issue? You can set the calculation. You can actually set the maximum number of workers inside the Gradle.properties. In our example, what we end up doing is we could have set something different for our local machines and the CI machines, because our CI machines have only 10 cores, and our local machines much better and 16 cores. We did not do that stuff. We just set with something little lower, and we said, okay, CPU cores, divide by 1.5. Again, that number is arbitrary. We just left enough room for OS processes to run. That's something to keep in mind when you decide what kind of workers you want to set. Yep. All right, so the next bottleneck, what you're going to be experiencing is unused dependencies. Unused dependencies, usually, they contribute to dependency resolution, right? Gradle still needs to resolve all of these dependencies declared in the build script. This involves calculating a dependency graph, Gradle calculating the dependency graph, resolving that dependency graph, so Gradle ends up spending time doing the job that is not needed, that is not contributing to the final output. Another thing it contributes to is downloading artifacts. If you don't have the caching enabled, right, and if they're not cached locally, let's say you added new dependency, right, that you didn't use, Gradle will still end up downloading. Doesn't matter. It's going to end up downloading. Next one is configuration time, right, because Gradle needs to evaluate all of those dependencies, whether they use or not. So this is where the time spent to configure adds up to the build time. And also the class path size, because each dependency adds to the size of the class path, and that needs to be handled during the compilation. So compilation becomes longer, because large class path ends up slowing down the Java compiler, and the compilation time might increase there. That's why there are unused dependencies can cause a lot of bottlenecks. There are also outdated dependencies that can cause bottlenecks and contribute to the slow build times. One of them is inefficient build processes, right? Because you have newer version of dependencies, often, like newer versions of dependencies often include these improvements and optimizations in the build processes, and when you use outdated versions, you might be missing out on those enhancements in place, which means you're going to have slower builds. The next one is increased resolution time. Again, because the dependencies, they depend on other dependencies that might be outdated in that dependency, what you end up doing is you end up spending more time, like processing dependencies of the dependencies in place and resolving them, because Gradle will need to check multiple repositories and identify which one belongs to which, right? So it ends up slowing down the initialization phase of the build. Another bottleneck is compatibility issue, right? As projects grow and evolve, maintaining outdated dependencies can lead to compatibility issues with other tools and libraries that have been updated. For example, Firebase, right? Like Firebase, if you have Firebase library, you might have maybe excluded some of the transitive dependencies that are inside the Firebase that, for example, OKHTTP, you might be on the old OKHTTP version, right? But your Firebase, the one that you updated, end up having a newer OKHTTP version. And you will experience this compatibility issue because of two different versions of OKHTTP. And Gradle still needs to resolve all of those stuff up front before it even begins to build your project, which adds up to the build time. And not to mention the deprecated features that sit and linger in the outdated versions, right? Because they require additional configuration in place, which takes time. And other reasons, obviously, if you have outdated dependencies, it also means there is a lack of support when, for example, if you file a ticket with some libraries and so on, right, and you say, what kind of version are you on? And they say, the first thing that they would say is, hey, have you upgraded to this version? Because we solved it, right? So that's what usually is, because oftentimes deprecated features will not be supported by the open source or any other libraries. And the solution for unused and outdated dependencies is to use automated dependency management, right? It's being solved already in the industry. We are Toast going to be enabling this end of this month or maybe early next month, who knows when the time gives us. The idea behind that, we're going to be enabling automated dependency management by using the plugins like Dependabot. Was it another one there in place? I forgot the name of it. Okay, so now going into remote bottlenecks. Outdated hardware, it is applicable for the local ones, local bottlenecks as well too. And then we also have container configuration, and plugin settings do affect heavily your build times. And inefficient scripts that you have in your CI. So when it comes to outdated hardware, I said it's remote, but it could be also local and all. Imagine running your code that you have right now, production code, on MacBook Pro 2012. Even with all of the updated versions that you have, like latest JDK and so on, it doesn't matter like how much you're going to have the most updated dependencies. If you run on the old machine, the build will be slow. The build will be slow. So upgrading machines is actually a very viable solution and very preferred. So is migrating to new agents and controllers, with the new hardware information in place. All right, when it comes to hardware, what we care most is CPU and RAM, right? CPU is brain and processor. RAM usually stores actively used short-term data, while CPU, with its number of cores, ends up processing all of that short-term data. So back and forth, that's how they play together, in a nutshell. The solution, especially when you build heavy Android applications, is that you need more CPU, more RAM, That's the answer. Make sure you buy new hardware with a lot of CPU and a lot of RAM. Well, technically not that a lot. You don't need to build them latest CPU with, I do not know, 40 cores and so on, like gaming CPU, stuff like that. It's not that important, unless you decide to run AI agents locally, maybe then. But until then, sweet spot would be somewhere between definitely a little over 10, 16, good. 32 if you're using very heavy something. And when it comes to RAM, you definitely want more than 32 gigabyte. And I'll tell you why you need more than 32 gigabyte. So when we're working and trying to identify what is the best XMX size, the maximum heap size that we can set to our project that will not just run good, right? Like it's not just going to run out of memory, but it also will help us not to waste resources in our agents. What we found is that this little bit of calculation might seem too much, but I spent last night thinking about how can I actually put together this information that could be as helpful. One thing to keep in mind, our project, we do have modules, but our project is not modularized. There's a huge difference between them. So each heap size, like when you set a heap size inside the JVM args, org.gradle.jvm args, you're essentially setting a heap size for your daemon, Gradle daemon, right? Then you also have to keep in mind additional that JVM and OS overhead that you need to put inside your JVM memory, which is, as I said, somewhere around 30%, 30 to 10% that you have to allocate, right? So if, let's say, our XMS size is 10, right, like the heap size for our daemon is 10, the overhead will be additional 3 gigabyte that you need to add. Total will be 13 gigabyte. Now, one thing I forgot to mention about the max workers. When you don't set the max workers, and if you have a very hungry application and not well optimized, what might end up happening is that each worker will end up using all of the maximum available heap, right? So the number of workers that are running on different cores will end up taking as much heap as they can. Let's say if your heap is 10 and you have 8 workers, the total will be 80 gigabyte. But the reality is not all projects and not all workers end up using all of that heap. So that 30% on the line number 2 is number of workers at maximum heap at the same time that happens. That's how I did the calculation. Oftentimes it could be less or more, like you have to tweak for your project, which will work the best. So if you have 8 workers with heap size 10, and then 30% of them are always at the maximum heap usage, assuming that you have a very heavy app, right? The total will be around 24 gigabyte. And the first line we had 13 gigabyte, and if you combine all of that together, it's going to be, what is going to be? 13, 80, okay. Okay, I'm calculating here, spending some time. So, okay, so let's skip that part. Let's come back to it later on. Let's focus on the line number 3, because, so with the line number 3 is that we're combining the gigabytes from line 1 and line 2. We also need to keep in mind that each maximum worker that is taking up the core, right, will need as well the JVM and OS overhead, because you do not know, it still needs that JVM and overhead. So you're going to save that 30% to that overhead as well. So if you multiply, and let's say if you have XMX 10 gigabyte, maximum heap size at 10 gigabyte, and you have maximum workers to be 8, the total required memory for your agent should be around 45 gigabyte. That's the rough calculation, what we learned so far. Even then, we do hit occasionally, right now, out-of-memory issues as well, too, on our agent. It does happen time to time. So maybe we need to increase that memory. All right, so the next bottleneck. Because we use Jenkins as our CI, Jenkins has its own container where inside the container you can set up the nodes agents, which is basically hardware, and run the builds there. Container settings and configuration are important to pay attention because after you improved and optimized your local bottlenecks, what you might end up experiencing is that if your container is very old and bloated and have a lot of different plugins that are used across different repositories that are not related to your Android builds, it ends up, your project ends up paying a hefty penalty. So for example, the startup time, it could be very slow if you have especially so many builds coming up. Waking up those agents can be costly all the time. Like let's say in the back end, they do have, their builds are very fast oftentimes, right? Like it takes them 10 minutes, 15 minutes, and they can just boot up the agent, run the project, run the build, and then kill the agent. In the case of Android and mobile, you might need to rethink whether you can use the same methods that you use for your back end versus for your front end, for your mobile, not the front end. And then obviously, because there's a startup time happening, it all begins from startup time because you need to allocate the resources, wake up those agents, the wait time for your builds are gonna go up. And it also could be you're on an old instance like we were. Our Jenkins instance was from 2013, just in time when the company was created, right? So what are the solutions? Number one solution, you need to evaluate how many builds you have per day, how many builds you have per hour, because if you only have 10 agents available at any time, and those 10 agents end up waking up and just going to sleep every time when the build happens, it might not be optimal for you because with 150 builds on average day, your rest of the 140 builds end up queued up, and waiting for even begin building, right? So maybe that's the time for you to look at your agents and increase the number of agents that you need for your project. And the second solution would be keeping agents warm. Because our Toast POS app is very active repository, we have lots of builds happening almost at any hour. We are an international team, during the day, at night, right? What we notice is keeping agents warm pays off in the long run because the wait time is very, very low. So that's something for us that's something what we learn. And the third very viable solution is to migrate to new agents because when you migrate to new agents, new instance of Jenkins controller, you might get, first of all, the newer version of Jenkins that could be very optimized, for your settings. And it also means might not be as bloated as the old one. So migrating, again, is a viable solution, although my team member might not like it that very much, especially she's done it a couple times. Okay, so besides the container configuration stuff, within the Jenkins world, we also have plugins. Think of them as dependencies. I do not know, right? So we have plugins, and you need to modify those plugins and tweak them, right? Because if you don't tweak the plugin settings, what you end up having is you end up having build queue congestion when you have 100 builds queued up and waiting for the agent to become available. And you might also experience, that builds keep getting triggered every time you update something in your PR description, right? So what happens is that, here's a story about this part. Our builds would get triggered every time when someone updates any kind of PR. But on top of that, because our infra team, mostly back-end infra team, what ends up happening, they had a philosophy of running every commit at all time, like running every commit and running every commit. Like, every commit is equal to the build, and everything needs to be built, right? And obviously, the build queue ends up being very long. And every time when someone updates something, even with the same commit, right, that build ends up being added to the queue. And hence, the builds end up being very slow. So this was an interesting learning. And what we did about this stuff, we end up installing actually build avoidance plugins in our Jenkins. So the builds are not going to get triggered anymore every time when someone updates the PR title or someone updates the PR description, because by default, GitHub ends up sending all of the events to our Jenkins, and modifying what kind of events need to be sent to Jenkins is not an easy solution on the GitHub settings site, apparently. So what we end up doing, we end up installing a plugin, build avoidance plugin, and we were able to configure it on our Jenkins container for that. And the second solution, what worked best for us, is canceling ongoing builds after the new commit is pushed. Let's say if developers usually commit something, they push the new changes, and then because the build takes this long, very long, it's enough time for them to fix the lint and push out that change again, and you have two commits queued up, which doesn't make sense. In reality, they're not gonna be building off of a specific commit in the PR, but rather they're gonna be building off of a PR itself, right? So it's gonna be off of the merge commit rather than a PR commit. So what we end up doing is we end up canceling ongoing builds if a new commit is pushed in the PR. It helped us to reduce that build queue by almost more than half. Cannot say exact numbers, but it helped us a lot. With all of these changes, we were able to reduce our build time overall Toast, but we decided to go further and see, is there something else we can do? Within the remote, within the Jenkins, what we learned is that our CI scripts were not optimized well. They were written back in 2016, 18, and they were not optimized very much, so they were not revisited. So we decided to give some love to those scripts and update them. What we noticed is lots of stages were serially executing one stage after another stage. That was one of the bottlenecks. We also had a lot of staggered Gradle tasks. Let's say if you have a stage that runs tests, only then we're gonna be running, like compiling the test tasks, in a test builds, only then. Or like, let's say if you have a espresso test, then only then we're gonna be compiling the app itself. And also another bottleneck was we had random timeouts on different plugin responses. One of them is Sonar Cube, for example. We had a 1 minute response, 1 minute timeout for response. So basically, even if the response came back within 5 to 10 seconds, the build would spend 55 seconds doing nothing. That was the solution, right? So we needed to update all of those scripts. And what we end up doing is we end up parallelizing a lot of stages in our app, including build stage, test stage, right, like espresso unit test stage, and also publishing all of our check styles. And just simply investigated and reduced timeouts across different scripts to see whether that timeout is still applicable right now in this script. That was one of the changes we made. And obviously, combining logically related Gradle tasks all together. Let's say if you're going to be assembling builds, makes sense to combine all of them together, not separately saying development debug is here, production, pre-production debug is there, and so on. Just combine all of them saying assembling a build, which helped us tremendously to reduce the build time. And to recap, what we did is for the local one, we enabled parallel, we enabled caching, optimized memory config, managed Gradle workers, and on the remote side, upgraded hardware, optimized container settings, fine-tuned those plugin events that come to us, or decided to go with additional plugin that will help us to fine-tune original plugin events, and just improved CI scripts, right? And with these changes, what we've gained, if before second half of 2023, before we began the work, our average build times were 68 minutes for the PR, right? After the H2, what we end up having 39 minutes average build time. We got 43% win. But last quarter, we decided to keep on pushing. We said 39 is not good enough. Let's try what we can do. And we end up going down to 27 minutes right now with 31% reduction. And in total, we had 61% reduction in build time. And that's the story of how we reduce build times at Toast. POS app. Yeah. And so there's a list of different plugins and tools that you can use to analyze your Gradle build stuff, like dependa but renovate if you want to automatically update the dependencies and set up Gradle Profiler and Gradle Process plugin to understand what's going on behind your builds and understand the Gradle processes under the hood. And resources, references, that's it. Thank you so much, everyone. Just in time, 3:15, I made it.